an amateur astronomer noticed something unusual in solar observation data, a faint smudge moving through space. That smudge turned out to be a brand new comet heading our way that we're now calling Comet R2 Swan.
A comet has just erupted near the Sun, its brightness leaping overnight and its tail fanning wider than 5 full moons. Days later, the Sun unleashed its mightiest flare in months, blasting a massive wave straight toward the region of space where Comet R2 Swan is now hurtling toward Earth. On October 21st, Swan will make its closest approach, coinciding with another interstellar object passing in near-perfect alignment. With solar storms set to collide with the comet's vast tail, uncertainty grips the scientific community. Will the sky erupt in a spectacular display or descend into eerie silence? The chain reaction has begun. So, what happens when Starfire meets a cosmic visitor? On September 12, 2025, Comet CR 2025 R2, now simply called Swan, rounded the Sun at a distance of just half an astronomical unit, closer than Mars ever comes to Earth. At first, the readings appeared ordinary, a faint object of magnitude 7.4, its tail stretching modestly across 2 degrees of sky. But comets are built for surprise. Just 2 weeks after perihelion, Swan's glow surged dramatically. On September 26th, amateur astronomers in Japan and Australia reported a sudden leap of nearly a full magnitude, pushing Swan into naked-eye visibility under dark skies. By day's end, international forums were alive with data confirming a sustained brightness around 5.7 to 5.8 through September 28th. This wasn't a statistical blip, it was a sign of internal upheaval. The comet's frozen nucleus, weathered by millennia in deep space, was now cracking under solar heat. Subsurface gases burst through the crust, dragging dust and ice outward, swelling the coma and feeding the tail. The effect was immediate. Light curves deviated from predictions, hinting at venting, structural collapse, or even new jets forming near the nucleus. Observers noted faint, jet-like streaks, possible fractures or vents opening in real time. Swan's behavior no longer fit the standard cometary playbook, attracting global attention from professionals and backyard astronomers alike. Its inner engine was exposed, its next moves unpredictable. The key question became not only how bright it might grow, but what the unleashed energy would do to its structure and to the enormous tail now streaming behind it. Stretching more than 2.5 degrees across the night sky, 5 full moons end to end, the tail transformed Swan from a fuzzy speck into a celestial spectacle visible even from suburban skies. That immense scale meant more of the comet's secrets were on display. Dust knots, shifting rays, and the faint electric blue of the ion tail painted a living portrait of solar interaction. The dust tail, heavier and slower, fanned out in a sunlit arc, while the ion tail, lighter and volatile, could twist, ripple, or even snap under solar wind pressure. Nightly observations revealed constant change, a new plume, a sudden bend, or a brief brightening as material vented from the core. Across continents, the global comet community responded in unison. Amateurs stacked long exposures, compared photometry, and shared time-lapse sequences that captured tail motion hour by hour. Subtle color variations, icy blue ions and golden dust, hinted at the complex chemistry within. Swan's position low in the southern sky during September and October favored observers in Australia, South Africa, and Argentina, though northern watchers would soon get their turn as the comet climbed higher and the moon waned. For anyone with binoculars, the next few weeks promised a rare front-row seat to a live experiment in solar system physics. Yet the spectacle came with uncertainty. The comet's immense tail now sat in the crosshairs of the Sun's next move. That move came on September 28 at 8:43 Universal Time Coordinated, when the Sun erupted with an M6.4 class flare, its strongest in months. Solar activity had been calm for weeks, with X-ray flux readings flat across GOES satellites. Then, suddenly, the instrument spiked. The flare's energy output, measured in millions of kilowatts, lit up GOES 16 and GOES 18 charts in real time. At NOAA's Space Weather Prediction Center, physicists scrambled to analyze the event, cross-referencing data from NASA's Solar Dynamics Observatory and SOHO's coronagraphs. This was no minor flay. M-class eruptions occupy the middle tier of solar intensity, but an M6.4 is strong enough to demand attention from satellite operators and forecasters. The flare originated from active region 4232, a sunspot cluster with a twisted magnetic field, located in the same solar quadrant Swan was approaching. Within half an hour, coronagraphs confirmed a coronal mass ejection, CME, launching outward at speeds between 800 and 1,000 kilometers per second, among the year's fastest. Inside mission control rooms, alerts rippled out. Teams checked radiation protocols, but this CME wasn't Earth-directed. Instead, it was headed straight toward the region of space occupied by Swan's expanding ion tail. The timing, just 2 days after the comet's dramatic outburst, was impossible to ignore. Scientists began modeling potential intersections between the CME and Swan's luminous wake. The data told a clear story. An M6.4 flare at 8:43 Universal Time Coordinated, a fast-moving CME, and a comet with a tail spanning more than 2 degrees, all converging in one sector of space. The Sun, dormant for weeks, had suddenly fired a powerful pulse directly into the comet's path. The overlap was extraordinary, and from NOAA's prediction center to small observatories around the globe, every telescope and detector turned to watch what might happen when the full force of solar fury collided with a comet's fragile heart. Top of form, bottom of form. Traveling at nearly 900 kilometers per second, the coronal mass ejection was fast enough to cross the Earth-Sun distance in less than 2 days. Its angular width, measured at about 90 degrees, placed it among the broader ejections of the year. But its direction was the real story. This time, the blast missed Earth by a wide margin. Instead, model overlays showed its main lobe sweeping through the sector of space now occupied by Comet Swan. For forecasting teams, the challenge was one of geometry. Solar ejections rarely travel in perfect straight lines. They expand, twist, and sometimes fragment as they plow through the solar wind. To trace the CME's path, scientists stitched together coronagraph images, plotting its leading edge against the known positions of planets, spacecraft, and, for the first time in years, a comet with a tail longer than 2 degrees. Swan's coordinates, just inside Earth's orbit and slightly south of the ecliptic, placed it near the predicted corridor, though uncertainties in three-dimensional modeling persisted. Without a direct Earth impact, in-situ plasma data would be scarce, leaving ground-based and orbital imaging as the main tools for tracking the encounter. Every major forecast center flagged the event for comet researchers, all asking the same question. Will the CME's broad front actually intersect Swan's tail, or sweep harmlessly past? The best estimates placed the CME's arrival near Swan between 48 and 72 hours after launch, depending on its true trajectory and speed. Density projections suggested a moderate event, enough to disturb the ion tail, but unlikely to cause any effects on Earth. For us, the risk was minimal. For Swan, the incoming solar plasma set the stage for a potential skyward drama, tail kinks, disconnections, or rapid structural changes visible within hours to anyone watching the right patch of sky. The instruments were ready, data streams open, and all eyes shifted to the comet corridor. Magnetic fields would now decide Swan's fate. When a coronal mass ejection like the one launched on September 28 sweeps through space, it carries a tangled web of magnetic field lines, each with its own orientation. A comet's ion tail is made of charged particles stripped from its nucleus and pushed away by the solar wind. These ions don't drift freely. They cling to magnetic field lines, forming invisible tethers stretching millions of kilometers behind the comet. The real drama begins when those lines meet the boundary between the comet's tail and the oncoming solar wind. If the CME's embedded magnetic field points southward, opposite to the usual field direction near the comet, conditions become ideal for what physicists call magnetic reconnection, the cosmic equivalent of a circuit breaker snapping open. Magnetic field lines collide, snap, and rejoin in new configurations, releasing immense energy and slicing off entire sections of plasma. In practical terms, this means Swan's tail could literally break away in minutes. a glowing fragment drifting off into space while a new tail begins to form almost instantly. The orientation of the CME's magnetic field, particularly its BZ component, would determine the strength of the effect. A southward BZ increases the likelihood of a tail disconnection. A northward one might pass with little more than a ripple. The process unfolds quickly, often within hours, leaving behind kinks, fading plumes, or detached ion clouds drifting independently. For theorists, it's a rare chance to watch magnetic reconnect ion unfold on a cosmic scale, far beyond any laboratory experiment. Every twist, bend, and break would be written across the night sky in real time, and every hour would matter. Swan's ion tail, over 2.5 degrees long, was fully exposed to the solar wind's power. If the CME's magnetic field lines intersected its path, the tail could kink or snap in as little as 90 minutes, a phenomenon that usually occurs unseen in the far reaches of space, but now potentially visible through backyard telescopes. Spectral signatures might shift suddenly, with hydrogen and oxygen emission lines drifting by up to 50 kilometers per second as the plasma responded to the impact. Morphological changes could happen faster than a feature film, a bright filament breaking free or new tail forming in the wake of a disconnection. This was science in real time, and some of the best data might come not from observatories, but from citizen scientists with cameras and clear skies. Still, experts urge caution. Not every flicker, ripple, or dimming could be attributed to a solar storm. The CME's exact geometry remained uncertain, and predictions of a direct encounter were still only hypotheses. Vigilance, not certainty, was the order of the day. The call went out to document, compare, and share observations, building a global record as the comet's story unfolded. For now, one truth remained. The only guarantee was change. The next anomaly could appear in a single frame, and the world was watching together. Then came the date that everyone circled, October 21st, 2025. The numbers told a compelling story. Swan would pass just 0.25 astronomical units from Earth, about 39 million kilometers, or roughly 100 times the distance to the Moon. For a comet, that's a remarkably close approach. And this was no random coincidence. The geometry lined up almost perfectly. Swan's orbit crossed the ecliptic at a shallow angle, moving through the same invisible plane that governs most of the solar system's traffic. Its position, just south of the ecliptic, placed it directly in the active zone of the solar wind and the heliospheric current sheet. On the very same day, interstellar visitor 3I, our Atlas, would reach Superior Conjunction, directly opposite the Sun from Earth's viewpoint, while Swan swept through its closest point. Though separated by millions of kilometers, both objects shared the same broad corridor of space, offering a rare side-by-side comparison between native and interstellar dynamics. For orbital analysts, such an alignment was a statistical near-impossibility. The odds of two unrelated bodies, one born in the outer solar system and one from interstellar space, converging near the ecliptic within days, were astronomically low. The timing only deepened the intrigue. October 21st would also bring a new moon, the darkest skies of the month, giving observers the clearest possible view. As Swan drew closer, even modest backyard telescopes could detect parallax shifts, tiny changes in apparent position as seen from different points on Earth. Sky charts showed the comet climbing higher each night, its tail sweeping gracefully across the southern constellations. The gap between Earth and comet shrank to a mere quarter of the Sun-Earth distance, offering an unparalleled window before Swan began its retreat back into deep space. For observers, timing and preparation were everything. October 21st was a headline date, closest approach, new moon, and pristine dark skies, but the viewing window extended across the following weeks. Swan's path, just south of the ecliptic, carried it higher each night through the southern constellations. From Buenos Aires to Perth, the comet would rise before dawn and linger well into morning twilight, its tail sweeping west across the horizon. In the northern hemisphere, visibility would gradually improve, with Swan peaking above the tree line after midnight and gaining altitude nightly. Star charts placed Swan near the border of Grus and Pisces Austrinus, easy to locate by tracing a line from Fomalhaut, the region's brightest star. With its 2.5-degree-long tail, the comet's luminous trail could be measured against the gaps between nearby stars. For binocular users, a standard 7x50 field of view captured the entire tail in one sweep, while small telescopes revealed intricate structure and color gradients. Even a tripod-mounted camera with a few seconds of exposure could record the streak. As Swan closed in, the parallax effect became measurable within hours, letting observers across continents compare coordinates and refine trajectory models. Amateur astronomers coordinated globally, logging rise and set times, stacking images, and sharing overlays to track the comet's nightly evolution. The checklist was simple: note the comet's position, record the light, and keep watching. Top of form: sketch or photograph the comet's tail, and watch closely for kinks, sudden brightenings, or fading. Every observer, whether standing under city lights or rural darkness, adds a pixel to the global picture. This is the moment to join the watch. The timing is extraordinary, setting up a documented encounter between solar and cometary forces. As Swan nears its closest approach to Earth on October 21st, at approximately 0.25 astronomical units, scientists are on high alert for direct effects between the coronal mass ejection and the comet's ion tail, a phenomenon known to trigger rapid and visible transformations. Yet, the exact outcome of this solar-comet interaction remains uncertain, with no confirmed connection between the recent solar flare and Swan's earlier outburst. What is certain is that this October, both amateur and professional observers share a unique window to witness cometary and solar dynamics unfolding in real time. As recorded through the Global Observation Campaign, Swan's journey offers a rare opportunity to watch cosmic forces in motion, with its final results and mysteries still unfolding before our eyes.